At this point, we've defined angular momentum for both classical and quantum systems, we've expressed it in Cartesian and in spherical polar coordinates, and we've determined its eigenvalues and eigenfunctions, the spherical harmonics. I want to close with saying a few things about the relationships between various angular momentum operators, because it turns out these are universal relationships that will hold no matter whenever we have angular momentum as part of our system. So, for example, we're going to go ahead and use our Cartesian coordinate definitions for the three components. So y pz minus z py are Lx. Ly is equal to z px minus x pz, and Lz is equal to x py minus y px. Now I'm going to have to write a lot of operators in what's come, so I'm going to beg your indulgence not to keep writing the little hats over them. Everything I write now is going to be an operator, so if you would please just agree to that, then I will stop writing all these little hats. What I do have, though, is we're going to need these commutator relations. Okay, the commutator of x and px is equal to IH bar. That's also equal to the commutator of y and py and the commutator of z and pz. So these are going to be very useful in the sorts of things that I want to now show that are relationships between the angular momentum components. So, for example, let's suppose that I want to determine the commutator of Lz and Lx. So what would I do? Well, I'd use these expressions for Lz and Lx. So Lz is xpy minus ypx. Lx is ypz minus zpy. And then whenever I have something like this, this is going to break down into several components. So I'll have one commutator that will be this with this. So I'll have xpy and ypz. I'll then have a commutator of xpy and zpy. So I'll have minus, because there's a minus sign here, xpy zpy. Then I'll have minus ypx ypz. And finally, I'll have minus ypx minus zpy, so that'll give me a plus ypx zpy. Now, whenever you're faced with a bunch of commutators like this, it could be a lot of work, or it might be that there's several of these you can recognize right off the bat are going to be 0. For example, x commutes with both z and py commutes with both z and py, so this one is going to be 0. Y commutes with y commutes with pz, px commutes with y, and px commutes with pz, so that one is also 0. What about these other two? Well, I've got a py and a y, and I know that one won't commute. Over here I've got a y and a py, so I know that one won't commute. So if I write these out, and I can pull the x in front, because it's on the front edge of this, py, y, pz, I'll end up with this whole commutator is basically equal to this one commutator with x and pz bracketing it on either side. And then for the other one, I'll have y and py are the parts I want to keep. I'll have a z, y, py, and a px on the other side. All right, so this is the one I want to keep. Well, ypy I know is IH bar. This one is minus IH bar because I've got them in reverse order. So now when I write that out, it'll be IH bar times this term zpx minus xpz. Right, which is just the commutator. I'm sorry, it's not the commutator. This is just the definition of Ly. So in other words, I have shown the result that Lz, Lx, the commutator of those two, is just equal to IH bar Ly. I could similarly show that the commutator of Lx, Ly would give me IH bar Lz. And I could also show that the commutator of Ly, Lz would give me IH bar Lx. Notice there's a cyclic permutation here. XYZ, XYZ, XYZ. All right, they're circulating cyclically. All right, so these commutation relations are going to be found in all systems with angular momentum. Now, I'll say that you can also show using this that L squared, say Lx, is going to be Lx squared plus Ly squared plus Lz squared, Lx. The Lx squared is going to commute with the Lx, so I don't have to worry about that one. So I'm left with two commutators. One is Ly squared Lx, and one is Lz squared Lx. And it turns out that these will end up giving me the negative of one another, and so when I add all this up, I will end up with the result that the commutator of the whole thing is just equal to 0. And this is also going to be true, by the way, for the commutator of L squared with Ly and the commutator of L squared with Lz. So this may raise some questions. All of these things commute, that is to say their commutators give us 0, so doesn't that mean they all share the same eigenfunctions? Well, let me make a little bit of a summary here on the last slide. All right, so one, what these things indicate is that L squared can share eigenfunctions with any of Lx, Ly, or Lz, okay, because it commutes with all of them. But 2, since the commutator of Lx, Ly is not 0, and the commutator of Ly, Lz is not 0, and the commutator of Lz and Lx is not 0, that none of these can share eigenfunctions with the other two. So how do we resolve this? Well, the way we resolve it is that we say that L squared shares eigenfunctions with one of the components, but not the other two. And we usually denote the one as Lz. So Lz and L squared share eigenfunctions. And we've already shown that they do when you write them out in spherical harmonics, in part because Z is treated a little bit differently mathematically than X and Y, and so it becomes the one that naturally shares eigenfunctions with L squared when they're all written in that particular coordinate system. But we could find another coordinate system which might allow Lx to share eigenfunctions with L squared. But this is how we generally deal with angular momentum type states and with angular momentum operators. They all have these particular properties, and we typically say that L squared shares eigenfunctions with Lz, but not the other two.